Thank you very much for the invitation and the opportunity to give these talks. Of course, it's difficult for me to adjust the level. So I might be too low or too high. So you have to.
Beginners,
so I decided to start with the beginning.
okay.
So today I would like to give you an overview on results on Tate resolution. On projective space. So this is all work, things we started out in the 70s with Bernstein-Gelfand in Beilenson. I didn't know about these things, but I didn't really appreciate the exterior algebra as one of the central objects in projective geometry. So we all know that the polynomial ring is central for algebraic geometry. So if notation, I work of an arbitrary field k x0 up to xn, which also will be the symmetric algebra with a homogeneous coordinate ring. Of Pn P of W. So we all know that sort of modules over this ring S correspond to Courant sheaf. So M graded. So S module. Then M represents finally generated, say. Then M represents a coherent sheaf. So M tilde, which I frequently give it a note by F, is a coherent sheaf. On Pn. So we have graded modules, S modules, finitely generated, and so you have M, we can send this M to M tilde, a coherent sheaf. So of course, how to describe a module M? Well, one way is to give it via generators in relation, to have a presentation. To get more information of M, we would maybe compute the finite free resolution following Hilbert, have the Hilbert polynomial, the Hilbert function, which gives us the Euler characteristic of the corresponding sheaf and things like that. So we all understand that projective geometry it is very important to study free resolutions over the symmetric algebra. What's not so clear, or not so popular maybe yet, is that equally well are modules over the exterior algebra important. So the exterior algebra, so I will denote the dual space of W with V. And the basis, if I need a basis, it will be E0 up to En dual to x0 up to xn. Then we can look at E the exterior algebra. Here's V. And modules P modules P over E. They also finitely generated. Say finitely generated. Yeah, and also graded, of course, graded. We can also look at syzygies of P. For example, we can take P, a module finitely presented by, say, E0. This should be graded modules. So this here, the module here really is an E mod E0 of E, right? And I should take a grading into account. Now, these here, they're in degree 1. So, of course, I have sort of the map from V tensor W to K, which is just contraction. Or I have also the map in the other direction, the trace. Inside here I have the sum over the EI tensor XI, which corresponds to the identity. So if I view this here, so this map here, the pairing, I have this element in here, which I can view also as an element in, say, this is an homomorphism from W to W, right? So, and inside here I have the identity map. This is given by that element. Clearly the identity homomorphism has degree 0. So I will give, for no good reason, these elements EI is a degree -1. So lambda R of V then sits in degree minus R. Minus R, right? But this is minor. I mean, we could, this is a choice which works out a little bit better. If I do this, then some slightly surprising, I better put here a 1 because it maps the generator, which is in degree -1, with multiplication in 0 into element E0, right? So one big difference is between the polynomial ring, where we can present a module, it has a finite free resolution, it's finite syzygy, so there's a finite computation giving us a free resolution. Now if we do this here, what is the kernel of this map? Multiplication by E0. Well, E0 which E0 is 0, so the kernel of this map is again given by E0, and it is then plus 2, right? So maybe for that reason, and of course now continues forever. So this process doesn't stop. So syzygies over the exterior algebra are maybe not so finite, right? So that might be a reason why they're not so popular to consider syzygies over the exterior algebra. What I would like to try to do is to convince you that there is a very good reason to do so. So first, we have the basic idea of Bernstein-Gelfand. Which associates to graded and to graded E module P F your finitely generated and graded finitely generated E module P, a bounded complex. So we can take P0 tensor O of sheaves or S modules of free sheaves or S modules, and we'll write down both versions. So first this one. So we can multiply by our element some EI tensor XI. Then this will end up in O of 1, and the EI will lower the degree in the P, and before, of course, we have sort of a P1 tensor O of -1, and there we have some EI tensor XI. Now the composition here, composition is 0. Because the multiplication with the multiplication in the symmetric algebra is symmetric, but the multiplication in the exterior algebra is skew-symmetric. So this is a map which is both symmetric and skew-symmetric in a certain sense, so it has to be the 0 map. If we just compute. How does this map go? Well, it's given by, so we have sort of the product sum ei tensor xi times sum, using new indices xj. Then this will be given by multiplication with some ei wedge ej tensor xi times xj, multiplication by such an element, and I sum here over all ij, but of course they occur in pairs, and the so this is the same as the sum I less than j ei wedge ej plus ej wedge ei times xi xj, and this of course is 0. So this is a complex. So here we have a complex. So this I call this the functor L. So L is a functor from E modules, graded E modules, to linear complex S complexes. Well, I really don't have to use O here, I could use S instead. So I send a module P to the complex P0 tensor S, P minus 1 tensor S plus 1, and so on. P1 tensor S minus 1. So this here is the complex. This here is L of P. So Bernstein-Gelfand looked at this construction in their attempt to construct vector bundle on projective space. In the 70s, the construction of vector bundles, or the classification of vector bundle on projective space, was a very hot topic. There's this famous conjecture that rank 2 vector bundle on P6 splits at the direct sum of line bundles, 2 line bundles always, which is unproven for, nobody could do anything. The construction of vector bundles was sort of a deal, just have to have examples. They were sort of in the 70s a new tool, right? Now, so what they would do, for example, is take this complex, sheafify, and take its homology and hope that that is a vector bundle. Then we need rather special objects. All right. So if we find nice P modules, P minus P1. P is a graded module. P is the direct sum of P, D, and Z. Of course, if P is finitely generated, only finitely many are non-zero. So this is a bounded complex, right? And then you might ask, what kind of modules P are going to have be a complex which has homology, one chiefify. So I could do the question they had, what kind of modules P give a complex, well, L of P, maybe tilde, which has homology H. Well, I wrote it cohomological, so maybe I wrote H tilde of L of P equal to H0 of L tilde P equal F, a vector bundle. And the main result was that any vector bundle can be obtained in such a way. And they characterize modules P which lead to vector bundles in terms of syzygies. We're going to see that later on. So that was their paper. Now the idea to look at a P module as a complex can also be applied to S modules. So what we have also functor R, which goes from S modules to linear complexes of E modules. So if you have M equal the direct sum of MD, a graded S module, we can form MD tensor. I'm going to change this later on. I do it just sort of to have the similarity. First I can do this, and then I can go to E of -1 tensor M D plus 1 and so on. So this is a complex of three, this is a sequence of three modules. So, I mean, what really is a module? A module M is sort of, is a direct sum of vector spaces plus maps mu d, which explains the multiplication. So from W tensor MD to W tensor MD plus 1, right? And of course, they have to satisfy commutativity law, not arbitrary sequence of map. So I'm now going to take an extremely naive point of view. A module for me is just a direct sum of vector spaces together with multiplication maps. And then, and this here, we can flip. This is the same. Think as an MD to MD plus 1 tensor V. So this is the same tensor. And this I can look as a matrix of linear form. So this is gives is a linear matrix from E tensor MD to E tensor MD plus 1. And I should put in a -1 here because it's linear. All right. So I get a sequence of linear matrices, and now the commutativity here can be expressed by the fact that this here is, if I do this twice, is a complex. And so the MUD define S-model structure, S equal sim W module structure, if and only if this is a complex. This is a complex. So like in this case, from a graded module we get a linear complex which we can chiefify and take its homology. That might be something interesting. Here we have a graded module and we get a complex. Now by the same computation as before, right? I mean, this, if I compose this, then really it means that the multiplication is commutative. Xi times xj times m is the same as xj times xi m. So we can see this on basis, yeah, I think I will leave it here. Now, of course, interesting graded modules which give sheaves, are non-zero in arbitrary large degree. So this complex will always be, for interesting modules, infinite, right? It will be an infinite complex. So this looks at first sight a little bit scary because it's so infinite. On the other hand, I mean, so there's a little proposition. There is a equivalence between graded modules. As modules M finitely integrated modules and left-bounded linear complexes. Of free modules over the linear algebra over E.
What is left bounding and left bounding?
Yeah, I mean, zero on that side, right? All right. If I don't assume finite generation, then there could be, I only need that all graded pieces are finite dimensional, then I get a free complex, right? Right. So this resolution is this direction. This resolution, if there would be exact, there could be an injective resolution, right? There would be no projective resolution. There would be naturally injective resolutions. So E is a very nice algebra. E is an algebra where injectives and projectives are actually the same. Free injective and projectives is the same. Right? So, of course, there is a difference between the injective hull and the projective hull of the residual class field. Right? The injective hull of the residual class field is actually omega E. So the E is the projective cover of K. There's an E module, right? It's it's maximal ideal, right? This was lambda V, right? Well, omega E, which is lambda of W, which also contains a copy of K, right, is the injective cover, is the injective hull. Right? So I mean, this algebra E is very nice. I mean, it's not commutative, I agree, but otherwise it's very nice. It's Bernstein. I mean, this is a free module, right? This is nothing else. This is isomorphic. Omega E, of course, as an E module, is isomorphic to x0 wedge xn times E. It's generated by x0 up to xn. The action is by contraction. The E x'd on lambda W by contraction. Right? So for that reason, because these complexes go in this direction, it would actually be better to replace E by omega E, because then we would have sort of the right objects for the injectives. So we're going to find R of a graded module M to be the complex hom E over K MD going to hom K E over MD plus 1. And of course, this is just the same as omega E tensor MD going to omega omega E twisted by how do I want this? I want this to be D, and then here omega E of D plus 1 tensor MD plus 1. Is this right? See, do I do this right? The signs goes down, so better have a minus D here. And goes down, right? And the map is defined as well. Of course, I also can explain how this is an E module. Of course, it's sort of the dual of E tensor MD. This is over K. And it's a complex of the same way. So we have this object here. So we have two functors, R and L. two functors. We have S modules are going to linear E complexes, and a map in the other direction which goes from E modules to linear S complexes. So this is S complexes. Of course, we could extend both of these things to arbitrary complexes. We could take complexes of S modules. Then we get a double complex of E complexes out of this construction, functorial. We can take the total complex and vice versa. And then sort of this induces a map from complexes of S modules to complexes of E. And then we get sort of this induces, so now we have R and L extended, and then here we get to the derived category of S and the derived category of E, and this is going to be an equivalent of category. I'm going to prove this. Now this looks very abstract, right? And at least for me it looks very abstract and maybe not so interesting. It's too abstract, right? Not concrete enough.
There is some guy who majored.
Oh, I understand. Yes, I completely agree with the point of view that the module category is much harder than the derived category, right? But you have to work a while before you admit that this is really true. Yeah, the derived categories are a little bit flabby, right? It's not so easy to say when two objects are really equal or isomorphic, right? It's very difficult to say. On the other hand, more objects become equal, so it's easier, right? So the point of view when people nowadays take is the derived category is an easier object than the module category. Now, I'm more into classical algebraic geometry, and there the module category, of course, plays a crucial role. Modules are coordinate rings of varieties, section modules of coherent sheaf, and so on. So I think for me this part here up here is much more interesting, and we will see how this comes about. So this was from the 70s, and Bernstein-Gelfand, and I think we should make at least two examples of these functors. We can take E as an P module, E module, and then from L of E. So this is of course K K. Then we have W tensor O minus 1. K tensor O. And it ends up with lambda n plus 1 W tensor O minus n minus 1. This is just a sheafified causal complex. The sheafified causal complex. And it is exact as a complex of sheaves. So free E modules do not give interesting objects in, remember I had a second step. After passing through this complex, I wanted to pass through the homology of this complex, and that should be my interesting sheaves, right? So this doesn't give us an interesting object. This is an exact complex, there's nothing. The other example is we could take R, look at R of S. So, how does this look like? I would like to write this down in terms of matrices. So I have one copy, I have omega of E, and then in the next term I have omega of E n plus 1 copies, and here I should have a minus 1, and then I have omega of E, and then there are, n plus 2, choose 2 copies, minus 2, and so on, right? And how does this matrix look like? So here it's given in terms of a basis by a column vector E1 up to En. And the next matrix here is going to be, that's a, if I wrote already, if I have to write this down explicitly, I already have troubles, right? I mean, it's too big, right? Let's do a very simple example. Let's do n equal 1. So we have E0, E1, right? And this is correspond to 1, and then we have x0, x1, and then the next matrix you have x0, x1, and then we have x0 squared, x0, x1, x1 squared. What do we get next? The next matrix is, I write it this way, is, this could go to x0, I get an e0, let's see, I multiply with e0, x0, plus e1 tensor x1, basically. So I get here I get an E1, here I get an E0. This, I'm confused. Is this correct? Oh, this doesn't look right. Here I get an E0, here I get an E1, here I get an E0, here I get an E1, and this multiplies to 0. This time this is indeed 0. Here, the middle. And the next matrix, what will be the next matrix? The matrix will look like a little larger. So we would have now, let's see, E0, E1, E0, E1, E0, E1. Will be the next matrix. This times that, and that is 0. This times this is 0, but also this times that is 0, and so on. So this here is sort of a little bit harder to write because I have so many variables. So maybe instead of that, we could look at something that has only 2 variables in it, but lives in Pn. So let's look at P1, and I map it to P3 as a rational normal curve. So x0, x1 maps to x0 cubed, x0 squared, x1, x0, x1 squared, x0, x1 cubed, right? And then, like, of course, I have the coordinate ring. My module M will be the coordinate ring of P1. So S mod the ideal of the image. So the image is the curve C. C is the rational normal curve. And we could do the same computation again. And see an easy pattern. We start out with 1, and we have the basis x0 cubed, x0 squared, x1, x0, x1 cubed. So here we have E0, E1, E2, E3. Now if we do the next matrix, we have x0 to the 6, x0, 5, x1 up to x1 to the 6. So I get here an E0, E1, E2, E3, and E0, E1, E2, E3. So now I have E0, E1, E2, E3, and then E0, E1, E2, E3. So this is now a 4 by, something is funny, a 4 by 7 matrix, right? It's 4 by 7. And the next matrix is of course, is a 7 by 10 matrix. Yeah. 7 by 10 matrix, and you can guess how it looks like. It looks precisely the same, right? It looks like that. So at least in this case we can do that. I would like to go back to the easiest example which we had. We had sort of this E0, E1 matrix, and then we had E0, E1, E0, E1 matrix in this direction, right? So with a complex like that. And now do what we do in normally we do projective resolutions. Right? So what's the kernel of that map? So yeah, I mean, I've taken a kernel. So here we have omega e, or a free E module if you want. What are generators of the kernel of this matrix? What's the syzygy matrix of that? So, well, I claim that it's sort of given by E0 wedge E1. E0 wedge E1 times this matrix annihilates this matrix, and no other matrix annihilate that. Right, so this is a quadratic map. Maybe I write it like that. E0 wedge E1. And then, so we have again here a free module. So this was omega E. And here we have another copy of omega E of plus 2. And then I can continue. Right? What's the kernel of that map? Well, that is given by E0, E1. And then I have omega E 2 copies. And the next map is the transpose of that map. So it's very, right? So actually, in this simple example, we can compute also the projective resolution. We can continue. I mean, if we now just continue. So, what is the meaning of these terms? That is sort of this first question. So here is the first theorem. M finitely generated graded S module. Then R of M grade equal to R is acyclic. For R sufficiently large. So we have our omega E twisted, I think was minus, minus R times MR, and this goes to omega E minus R minus 1 times MR plus 1, and so on. And the claim is that this is a resolution of the kernel. This is a resolution of a kernel P. So this is exact. So this is maybe sitting in PR. Right. So from M is sufficiently large, then this will be a resolution of its kernel. That's the claim.
What's PR?
PR is a kernel.
Kernel, okay.
So this is an E module. So, to come to the definition of the Tate resolution is we now take this E module and resolve it projectively. So we have then here a free module T. This was in T R minus 1. T R minus 2 and so on. This will be free module, so the T J will be direct sums of omega E twisted by K some numbers alpha J, okay. Alpha some number alpha let's say minus K to the beta JK or something like that, right? We could take such a resolution here, right? And continue. And now, if you splice this together, we have a double infinite complex T, which is a Tate resolution of MR? Well, this is the Tate resolution of F. Of F, the associated sheaf of M tilde. It really only depends on the sheaf, right? M is tilde is isomorphic to N tilde if and only if MR greater equal to R is isomorphic to N greater equal to R for R large enough, right? By Serre's theorem. Right. In the functor, we had this functor from graded modules. S modules. Graded, of course, always graded to sheaves, covariant sheaves. M goes to M tilde, and then if we truncate, this is M tilde truncated by R, because if we want to describe the sections, what is the section of M tilde in a basic open set dF? Well, these are the elements of M localized by F in degree 0. So we always can, so these are fractions M F to the K, right? With the degree of M is equal to the degree of Fk. And we can take larger denominators. We can take Fk plus 1, so we can make the numerator of the numerator to have arbitrary large degree. Everything will be represented by things of arbitrary large degree, so that's why these two things are equal. Right? All right. There also has a functor in the other direction. If we have F a sheaf, we can associate it to this gamma star of F, which is the direct sum, maybe a gamma star of F is the direct sum over all D H0 or gamma H0 of F twisted by D. Right? This in general will be not a finitely generated module, because if F has associated points, if the sheaf has associated points, then there will be sections in arbitrary negative degree. But in general, this will finitely generated, so we can improve this a little bit. We can do instead go back with F goes back to gamma greater equal to R of F, where this is by definition only the sections in degree greater equal to R of gamma D F, okay? Which always will be finitely generated, right? So we get a sort of inverse, but it's not quite the same, and we have it we have a choice of R, and okay, so this is inconvenient. Anyway, coming back to this theorem here, if we would truncate higher, then in the first few steps we would just put in whatever we had, because this is exact. So this really only depends on by the theorem, the complex T of F depends up to isomorphism, up to choosing basis. Only on F. So it's really an intrinsic object. Of course, if we take M, go to M greater equal to R, form this complex and go back, and then we get sort of maybe the beginning, this part of the resolution. But the end is missing, right? The end is missing. So I think the crucial thing to observe is the following. Theorem of Eisenbart, Floistad, and myself. The T of F has terms TE of F is going to be direct sum H I of F E minus I tensor, all right, it was tensor omega E, and now the degree should be the opposite sign, I plus E. This formula. So
What is small e?
E is the homological degree, as term in cohomological degree. In right, this is the upper index here.
Yeah.
Right. So this correspondence of Serre is in a sense incomplete, right? First of all, certain modules gives no sheaves, or the zero sheaf. The Artinian module of finite length give Artinian sheaves. And the backwards functor here only recovers part, sort of, if I think in terms of this complex, only recovers parts after a certain range, right? We miss half of the complex, right? If we only look at Serre's correspondence. If we look at the whole complex, then we don't miss anything anymore. And what we can see that every cohomology group of our covariant sheaf in each homological degree, so this is from I0 to N, occurs in a precise position. I can read off the cohomology of this sheaf here in, I'm over time, you should stop me. I can read off the cohomology of the sheaf by computing syzygies over the exterior algebra. And I think these explicit computational methods and also the insight which comes with it is the use of this Tate resolution. Thank you.